So our next unit will be around atomic theory and radioactivity and radioactive decay and nuclear physics, basically. Okay, so it's going to be broken down into 4 different subtopics. The first one we'll look at is radioactivity and particles. So these are the learning objectives. So just like in any other case, make sure you've got on top of these learning objectives, and if you're having any problems, come and discuss it. So let's first look at atomic structure. Okay, it's going to be linked a bit to chemistry, but we all love chemistry, so not a problem. Okay, so an atom is the smallest possible particle, and it consists of a central nucleus composed of protons and neutrons surrounded by electrons. And there's the image that you have of an atom, at least at GCSE level. Okay, there's a lithium atom. It contains 3 protons, 4 neutrons, and 3 electrons. So the atom will always have the same number of electrons and protons because the atom is neutrally charged. Okay, number of protons in an atom equals number of electrons. And then we deal with the nucleus. So chemistry deals with electrons. Physics tends to deal with the nucleus. And this is where atomic and mass number come into being. So the atomic number, also known as the proton number, is the of an atom is equal to the number of protons inside the nucleus. So all atoms of lithium have 3 protons in them. And the mass number, also known as the nucleon number, of an atom is equal to the number of protons plus the number of neutrons in the nucleus. Okay, so lithium has 7 neutrons, 3 protons, so its atomic number is going to be 3, and its mass number is going to be 7. 3 plus 4 equals 7. Okay, so that's the example there. Protons equal 3, neutrons are 4, electrons are 3. So lithium has an atomic number of 3 protons, a mass number of 7, 3 plus 4, because that's the number of neutrons and protons combined, and that is going to give you your mass number. So protons, neutrons, and electrons have different properties. Okay, so the proton is found in the nucleus. It has a relative mass of 1 and a relative electric charge of +1. P for positive, right? Neutron is also found in the nucleus. It has a mass of 1 also, and it has a charge of 0. It's neutral. Okay. So an electron is found outside the nucleus. It's going to have a relative mass of 0, okay, close to 0, and a charge of -1. Okay. Never invite them to parties. They're always negative. And we also, in writing nuclear equations, have to use the correct nuclear notation, which you probably used in chemistry as well. So an isotope of carbon consists of 6 protons and 8 neutrons. So what we do is rewrite that as carbon-14, okay? Because 6 plus 8 equals 14, which means that it's going to be the atomic mass, the number of protons plus the number of neutrons. So when you hear the word carbon-12, carbon-13, carbon-14, you know we're talking about the mass number. Okay, the other way you can write it is where you have the mass number on the top, the proton number at the bottom, and the element symbol is going to be on the side there. There we go. But we also have something called isotopes, which you should have touched on in chemistry. So basically, atoms of an element always have the same number of protons. Okay, so lithium always has 3 protons, carbon always has 6. However, the number of neutrons can change, and these are called isotopes. So the 3 isotopes of hydrogen are going to be hydrogen-1, the most common, hydrogen-2, deuterium used in nuclear power, and also tritium, also used in nuclear power. Notice it's hydrogen-2 because it has the atomic mass of 2, because it's got a proton plus a neutron in the nucleus, and hydrogen-3, tritium, has 2 neutrons and 1 proton. Okay, the number after hydrogen is the mass number of the isotope. So question 1. An isotope of uranium, which is a chemical symbol of U, consists of 92 protons and 143 neutrons. Give 2 ways of notating this isotope. So when I say notate, how would you write this isotope on a piece of paper using the short form that we've just learnt? Okay, so pause the video now and have a think about it. Okay, so what you should have found was that the mass number of uranium is going to be equaling the proton number plus the neutron number, so 235. So one way you could call it is uranium-235, which sometimes we discuss when we're discussing Iranian nuclear deals. Okay, and the other way you could write it is the following: 235 on top being the mass number, 92 at the bottom being the atomic number, and U being the chemical symbol. Okay, question 2. Determine the number of protons and neutrons in the isotopes shown below. Okay, so again, pause the video now and have a little think about it. Okay, so welcome back. So for A, 7 protons, that's the proton number, so it means that number of neutrons must be 6, because 6 plus 7 is going to equal 13. Cobalt, proton number 27. The number of neutrons is therefore going to be 33, because 60 minus 27 is 33. Gold, proton number of 79. And 197 minus 79 gives you 118. Okay, 239. Polonium is going to be 94, the proton number, and 145 going to be the number of neutrons. Okay, so apart from really small atoms like the hydrogens and heliums, most nuclei have more neutrons than protons. Okay, so an important concept, at least in radioactivity, is the concept of ionization, because radioactive particles can ionize. So what is ionization? So ionization occurs when an atom loses or gains one or more electrons. Okay, so when an atom loses electrons, it becomes a positive ion. Okay, that positive ion is also possibly known as a cation. Okay, and the way I'd remember that is that I'd make a little cat there. Okay, positive little cation there. Right, so here we have lithium, which we've looked at. So the lithium atom is uncharged because the number of electrons equals the number of protons. You take away an electron, it then has more protons, which are positive. So it means it's now positively charged. So when an atom gains electrons, it becomes a negative ion, also known as an anion. Rhymes with onion, which makes you cry, so it's negative. So there is a link, of course, between radioactivity and ionizing radiation. So the nuclei of some isotopes are unstable. Okay, the bonding between them is unstable. So they decay, and this radiation can cause the ionization, especially of the air around it. Okay, this is known as radioactivity, and we call the radiation produced ionizing radiation because it's radiation which ionizes. And radioactivity is a random process. You can't really predict if a nucleus is going to decay. And this was discovered by Henry Becquerel in 1896. That's why the unit for radiation is indeed the becquerel, which we'll discuss later. Right, so we'll now look at alpha, beta, and gamma radiation. Okay, so an alpha particle consists of 2 protons and 2 neutrons. Given the symbol alpha, it is strongly ionizing. Okay, so it creates lots and lots of ions as it interacts with the atmosphere. Then we have the beta particle, which is a high-speed electron. Okay, and it's a symbol beta. It's produced when a neutron has decayed into an electron and a proton. Okay, and it is moderately ionizing. And gamma rays are very high frequency electromagnetic waves, and we've already dealt with those in the last unit, and these are produced when an unstable nucleus loses energy. The type of radiation we will look at is known as an alpha particle. Okay, so an alpha particle is when the nucleus gets too big, too unstable, so it has to emit a particle to stabilize. And the particle it emits is going to be called the alpha particle, which is this particle right here. Now the alpha particle consists of 2 protons and 2 neutrons. Okay, so it's basically a helium nucleus. And it's given the symbol alpha. And the alpha particle is very strongly ionizing, in which we will show later. Okay, so that's the now your new stabilized nucleus, and that is our new alpha particle. And that is our first form of radiation that we will look at. Okay, so the next form of radiation is known as beta decay. Okay, which has the symbol, obviously, beta. Now what happens is usually that happens with smaller nuclei, okay, who want to become stable by basically removing a proton and a beta particle. Okay, so you can see that now. It's going to emit the high-speed beta, and it's going to also emit a proton. Okay, and that's going to increase the atomic number of the corresponding isotope that is formed. Okay, so just summarize that again. So if you've got a nucleus wanting to undergo beta decay, it's going to emit the proton and the beta particle, which also has the nomenclature of that because it has no mass, being a high-speed electron, and that's going to be, of course, the proton P+. Okay, which is essentially the decay of a neutron into a proton and a beta particle. Okay, so the last form of radiation that we will look at is known as gamma radiation. Okay, so gamma radiation is a very high frequency electromagnetic wave, which we looked at actually in the last unit. So if the nucleus wants to release energy, it emits it in the form of a very high energy electromagnetic wave, also very high frequency. Okay, these guys are very weakly ionizing. Okay, so let's watch that again. It's going to emit this radiation, which is in the form of electromagnetic radiation. Okay, very high frequency, and it's also going to be weakly ionizing. Okay, so it's not going to form many ions as it passes through the atmosphere. Okay, so that's known as gamma radiation, and the symbol for gamma radiation is thus. Okay, that's the symbol that we use for gamma radiation. The ionizing. So you can also measure the penetrating power of alpha, beta, and gamma radiation when you consider how far they can travel in terms of the atmosphere. So paper or a few centimeters of air stops alpha particles because they're quite big and slow moving. A centimeter of aluminium or about a meter of air will stop beta particle because they're quite high speed particles, and basically a centimeter of lead and about a meter of concrete should stop gamma radiation because they're quite high energy because of their high frequency. So one thing we must also look at is the penetrating power of the alpha, beta, and gamma radiation. So basically how far do these different forms of radiation penetrate into objects. Okay, so we'll first look at the alpha particle, which of course is the helium nucleus, 4E2. So as you can see, it's quite slow moving, it's quite heavy. Okay, it's got 2 neutrons and 2 protons. So it can only really travel a few centimeters in air, and it basically paper stops an alpha particle. So the next one we're looking at is the beta particle. Paper probably won't stop it. It's quite high speed. It's a small little electron. So about 1 centimeter of air will usually stop a beta particle, or about a centimeter of aluminium, or in this case some wood. Okay, and the final one, the electromagnetic radiation in the form of gamma rays. As you can see, it goes through paper easily, it goes through wood easily. So pretty much it's stopped by several centimeters of lead or about a meter of concrete in order to stop gamma rays. Okay, so they're quite high energy and quite fast moving, and they're very difficult to stop. So the deflection by magnetic fields also occurs. So an alpha particle in a magnetic field is going to basically go a little bit up, okay? So why is this happening? Well, alpha and beta particles are deflected in opposite directions because of their charges. So alpha is slightly positive, so it's going to deflect up, whereas the beta particle is going to go down, and because it is negatively charged, whereas the gamma radiation hasn't got any charge, so it's just going to go straight through a magnetic field. Okay. And because the alpha particle is much larger, it's deflected far less than the beta because of the size. And again, no charge for the gamma, so it's going to go straight through. It's also the different forms of radiation are affected by electric fields. So the alpha is going to deflect up in a negatively charge, go towards a negative charge, whereas the beta is going to go towards a positive because it's negatively charged. The gamma just goes straight through. Okay, and again, notice the deflection because the alpha particle is quite big. It's not deflected as much as the beta particle. Okay. So just to finish off the topic or the subtopic, just filling in the words. So pause the video now and go through the answers for yourself. Okay, so atoms consist of very small nucleus containing protons and neutrons surrounded by electrons. Atoms of the same element will always have the same number of protons, but different isotopes, as they have different numbers of neutrons. The atom of substances are unstable and radioactive. They may give off alpha or beta particles or gamma rays, and gamma rays are the most penetrating type of radiation, and alpha particles are the least. Okay, so let's going to look at different forms of decay in a little bit more detail. Okay, so alpha particles consist of 2 protons plus 2 neutrons, and they are emitted by some of the isotopes of the heaviest elements, okay, because they want to lose that mass. Okay, so basically what happens is that alpha particles consist of the 2 protons, so you're going to emit the alpha particle. Okay, an example of that is uranium-238. So what happens is that the 238 emits an alpha particle and leaves thorium-90, which is a lot more stable. And you can see the 2 numbers at the top add up to make 238, and numbers at the bottom add up to give you your number of protons. Okay, so the balance is the same. They aren't destroyed. Okay, so uranium-238 decays to thorium-234 plus an alpha particle. The points to note are the mass and the atomic numbers must balance on each side, as we've discussed, and the alpha particle can also be annotated as 4,2 helium. Okay, so question, show the equation for plutonium-239 decaying from an alpha emission to uranium atomic number 92. There it is there, okay, and again the 2 sides add up. Okay, beta decay consists of high-speed electrons. They are emitted by isotopes that have too many neutrons. Okay, so here we go. One of the neutrons decays into a proton and an electron. The proton remains in the nucleus, but the electron is emitted as the beta particle. Okay, so an example would be decay of carbon-14. Okay, so too many neutrons. So what it does is it releases the beta particle, okay, and forms the element of nitrogen. Okay, there we go. So the notes to make are the beta particle is negatively charged, therefore has an effective atomic number of -1, and the beta particle can also be annotated as the following there, electron basically. Okay, still the same, still interchangeable. Okay, so question, show the equation for sodium-25, atomic number 11, decaying into by beta emission into magnesium. Okay, so pause the video now and see if you can get that correct. Okay, so you've got sodium-25 going to magnesium-25. There's no change in mass, but you've got a number of a proton is formed. Okay, and you end up with a beta particle. Okay, so you end up making magnesium. Okay, final one is gamma decay. Gamma decay is the emission of electromagnetic radiation from an unstable nucleus. Okay, and we've got usually it also emits along with an alpha and beta particle. So the example being cobalt-60. So that emits basically gamma radiation. Notice, of course, that there's no change in the element, no change in proton number, and no change in mass number. Okay, basically it's just releasing excess energy. Okay, so it just goes into another form of cobalt which has less energy. Okay, so both alpha and beta decay cause an isotope to change atomic number and therefore an element. And alpha decay also changes the change of mass number. So for alpha decay, it's down by 2, and the mass number is down by 4. Makes sense because an alpha particle is 4, 2. And beta, up by 1, and the mass has no change. And gamma, there's no change and no change. Okay, so just to finish off your understanding, complete the following decay equations below. Okay, so just fill in the gaps. Okay, so what you should have got was, of course, cobalt. The mass doesn't change, but the atomic number goes up by 1 and -1 there for the beta particle. For radon, it's going to go to 88 from the periodic table. It loses 2 there, but it becomes 220 because the alpha particle has a mass of 4 and a proton number of 2. And the final one with beta decay, you've got 16 nitrogen going to oxygen plus a beta particle. So another example could be how lead-202 decays into gold. This doesn't really happen, but it's just a theoretical example. Okay, so this is the information you've been given, okay, with the different symbols. So basically you've got lead going to mercury and the alpha particle decay. Then we've got the mercury going to platinum plus alpha decay. Then we've got platinum going to gold and beta decay. So we end up with gold at the end. Okay, there are also other possible solutions to get you down to gold. Right, so just to finish off this unit, just choosing the appropriate words to fill in the gaps. So again, pause the video and see if you can get 100%. So when an unstable nucleus emits an alpha particle, its atomic mass falls by 2 and its mass number by 4. Beta particles are emitted by nuclei with too many neutrons. In this case, the atomic number increases by 1, but the mass number remains unchanged. And gamma rays consist of an electromagnetic radiation as emitted from a nucleus when it loses energy, often after undergoing the corresponding alpha and beta decay. Okay, so there's a few online simulations which you could try yourself to help you revise. And in terms of questions to further show your understanding, there are 4 examples there.